Hello everyone. So today we are going to start our class of the week 11. Today we are going to talk about stability condition for numerical methods for partial differential equations. Specifically today we are going to approach the diffusion equation and its stability condition using the method of lines, and then the von Neumann analysis. So consider the diffusion problem on the 1D space for x going from 0 until 1 and for the time going from 0 until 1. So U is some concentration, and we have that it satisfies this differential equation, where D is the diffusion coefficient, and this is the initial condition. So for time equals 0, our concentration starts accordingly to some function eta of x, and these both are the boundary conditions for all the time bigger than 0, and as it's called on the boundaries for x equals 0 or x equal 1. And just to remember, this kind of boundary condition is called Dirichlet. So we are fixating the solution on the boundaries. So in this, eta of x is the initial condition, and the function g0 and g1 are the boundary conditions, and the diffusion coefficient. So suppose that we are going to use some numerical method to solve this problem. So the Laplacian of U, we are using a centered approximation. Just remember that this is a second degree derivative, and therefore we need at least 3 points to do this approximation, and we are doing a centered one, so we are getting the point xi and a point on the right and another point on the left, and we are doing this approximation on time. So here we are for space we are using centered, so space we are using centered finite differences, and for time we are using forward Euler. Okay, this is an explicit method, which means that each un plus 1 can be calculated using the previous data, and in fact if we write un plus 1 in terms of the past terms on time, it can just be written like this. So now we want to make the question. So how good is this method for solving this problem in particular? What can we do to try to find it out? Of course, we want to know if the method converges. That is, if we choose small k and h are sufficiently small k and h. K is the time stepping, and h is the mesh grid size. So if we choose this small enough, according to some restriction, take into account the stability region, we expect that for many initial conditions it will behave like the original continuous problem. So by the theory, saying that the method converges means that if we take k and h going to 0 or small enough, the discrete problem would behave as the continuous problem. And by the theory, the method will be convergent if it is consistent and presents some kind of stability. So consistency, remember, we are talking about the local truncation error going to 0 as k and h going to 0. So it's about the local truncation error. And the stability is about the eigenvalues of the problem being inside of the stability region, which is related. We want this factor to be smaller than 1. This amplifying factor is smaller than 1, and therefore, as soon as we increase the time, we are having a convergent behavior. So first we are going to talk about the consistency of the method, and therefore for that we need to calculate the local truncation error. So a method is consistent if the local truncation error goes to 0 as k and h goes to 0. The local truncation error is calculated by substituting the exact solution on the method. So remember, the method that we had before was this one, equal h square, and here is like un I minus 1 minus 2 and I plus ui plus 1. And so now, so this notation here, for example, denotes the approximation of our solution at the time at the point xi and time t n plus 1. Okay. And remember that Tn plus 1 is Tn plus k, okay? And xi plus 1 is xi plus h, okay? So it's just the point xi and plus the mesh size. So we are going to substitute the exact solution here. So if on the method we have this equality, now when we substitute, so originally in the method we have 0 equal this minus that, but now if instead we substitute the exact solution, we would have the local truncation error. So that's what we do, and observe that here we do some Taylor expansion around the point uxt on time, and here it's here and here we are doing some Taylor expansion on space, okay? So for the first one, so u here is just short for u of x and t, okay? And then because we are doing this on time, we have k here, and the partial derivative, So this notation here is this. So u with this small t is simply del u del t at the point evaluated at the point xt, and this goes. So here we are going to have terms of the order of k to the fifth, and this was we are doing this expansion on space, and again this notation x ux is del u del x, and also like this is del square u del x square, and so on. And observe that here we have this sign minus here for the odd terms. Okay. Now we are going to substitute this tree expression in the local truncation error formula. Okay. And by doing that, at some you should do this as homework while you're watching this video. Just try to do this, and you have to use this simplification because we need to remember which kind of problem that we are trying to solve. And more one observation for simplicity, we are taking into account that our diffusion coefficient is equal 1. So the problem that we are trying to solve is del u del t equal del square u del x square, which is the Laplacian. And we are also having to, at some point, to getting the same result that I got here, you also have to use these facts. So we get by this that the method is first order accurate on time, and second order accurate on space. So how we can see that? We can see that the local truncation here has some terms on k and some second degree term on h. So we say that this is first order accurate on time and second order accurate on space. So we can see that for h and k going to 0, the local truncation goes to 0, and therefore the method is in fact consistent. Okay, so we showed, so for having convergence, we want to have consistency plus zero stability implies on convergence. So we already showed the first one, the method is consistent. Okay, now the question is about stability, or like zero stability is for initial value problem. So here it's another kind of stability, but is also related to the eigenvalue. So the question is whether the when we have some linearized problem, if the eigenvalues of this matrix would be in absolute value smaller than 0. So yeah, that's the point. So in order to show this stability, we are going to use something that's called method of lines. So in the method of lines, we transform our original initial value boundary problem, initial value and boundary problem. Okay, so we transform our PDE with the boundary conditions and initial conditions. Originally are like this. And we are going to discretize only on space. It means that this is a semi-discretization. So we are only discretizing the Laplacian. Okay, so we get a system of ODEs. So we have that for each I in the space grids, we have some ODE. Okay, so in total we have M ODEs. So we are just getting interested on looking at the discretization of the interval 0, 1 in the space. So we get a system of ODEs, and as you see, we can also write this system on a matrix and vector notation. So we can write it in this way, okay, where our matrix A, so this is our matrix A here. So here we have the diffusion coefficient, so it should be here, okay. And it's also here. So here is our matrix A, and here is our vector G, which is carrying the boundary conditions. I don't know if you remember, but we had that for U of 0 t, we have G0 of t, and U1 of t, it's equal G1 of t, okay. So we carry these conditions here in this vector G. So we can in fact write our ODE system in a matricial way, okay. So we know that from some classes ago how to deal with the stability theory for an ODE system, okay. So we know the stability theory for an ODE system, and now we can apply this theory to the ODE system obtained by the method of lines. So let's just remember what we did. So we had some system that was U1 line of t equals some function 1 of U1, U2 for instance, and then U2 line of t, and then it equals another function of U1, U2. So if this system is linear, we can write this system as like this: U1 line of t, U2 line of t equals some matrix A times U1 of t, U2 of t, and then we calculate the eigenvalues of this matrix, and for For having stability, we want that so this is the original ODE, okay, but then we apply some numerical method to solve this system of ODE, and suppose that we are using Euler method, and then we would get UN plus 1 equal identity matrix plus K A UN. And what we have seen from the stability theory is that for this method to be stable, we ask that the eigenvalues of this matrix here should be smaller than 1, and like only we can only allow one eigenvalue to be equal 1, okay. And if we have a nonlinear system, what we do instead, what it means that is these two functions f1 and f2, they would be nonlinear functions, and then we linearize our system around some point, and then we calculate the Jacobian matrix, and therefore we are going to look for the eigenvalues of this Jacobian matrix and ask it to be smaller than 1. Okay, so this we already know, we already learned this on the past lectures. Okay, and now we are going to apply this same approach to this system here that we got through the method of lines. Okay, so we expect the method to be stable if K lambda is inside of the stability region. That is, if this time step K multiplied by any eigenvalue lambda of A lies on the stability region of the ODE method. So if we want to use the ODE system using forward Euler's method, then we have this behavior, and using the hypothesis that A is a diagonalizable matrix, it is possible to decouple the system into M equations, remember? So using the eigenvalues lambda p of A, we can decouple the method, and therefore we to be in the stability region, we ask that for each eigenvalue lambda p of the matrix A to satisfy this condition. Yeah. Here is the same, okay, because the eigenvalue of the matrix Ki plus Ka, so A has some, it's would be the same as the eigenvalues of so it's the same to ask restriction for the eigenvalues of this matrix, or calculate the eigenvalues of the matrix A and ask for this restriction here. So let's see some example considering the ODE that we have seen before, the ODE system of the linearized. So just coming back, so we have this system here, okay. So let's just write it small here. So it's U1 line until UM line equal D divided by H squared, and then our matrix A is minus 2, minus 2, 1, 0, 1, minus 2, 1, goes until the end will be minus 1, minus 2. So it's a 3 diagonal system, matrix or system. And let's just consider it for simplicity that G0 equal G1 of t, that's equal 0, so it's just this. Here multiplied by U1 until UM of t. So considering this ODE system, we want to study the stability for solving it using the forward Euler's method, and therefore we should impose this, where lambda p are the eigenvalues of the matrix A, where A is this matrix here, and it is called circulant matrix. You can see this on the appendix of the Levesque book. So it's some special case of matrix. So the eigenvalues of this kind of matrix is given by this, okay? So we have m eigenvalues, and they are given by this formula, and then substituting this at here, the stability condition implies that this happens, or removing the absolute value, we have that it should be in the interval between minus 1 and 1, and therefore this should be between minus 2 and 0. So we are going to analyze separatedly the condition 1 and 2. So the function cosine is bounded on the interval minus 1 and 1. So the inequality 2 here so this inequality 2 is satisfied for all k, h, and p, okay? So this function is between minus 1 and 1. So if cosine is equal minus 1, so substituting here, we would have minus 1 times something. It's smaller than 0, something bigger than 0, okay? So this is positive. So we have that this inequality would be satisfied for any p, k, or h. Now let's look for the other. And now also for cosine is still here, okay? Cosine equal 1, it would be 1 minus 1, and it is also satisfied. Now we are going to look for the condition 1, okay? So if it is satisfied for the smallest value of the function cosine on the right, it will be satisfied for all the values. So the minimum for the cosine occurs for cosine of ph of p pi h equal minus 1. So we have minus 2 dk divided by h squared. It should be bigger then minus 2, okay? And therefore we get this condition here. So this is the stability conditions for D, K, and H. So if we want to use the forward-Euler method to solve the diffusion problem, we should be pay attention on this stability condition. So actually this is a quite restrictive condition. If you think about if you have a big diffusion coefficient, you would have to take really small time steps to make this condition to be satisfied. Yeah, really small time step related to the mesh grid, okay, size. Okay, so if we choose K and H such that the stability condition is satisfied, and using the centered finite difference on space, the forward-Euler's method applied to the diffusion equation will have a good behavior. It happens that to fulfill this condition, we have to take very small time steps K compared to space grid size H. So maybe it is not the best method to solve this problem. The Crank-Nicolson method, which is just the Crank-Nicolson method is when we use this centered finite difference spatial discretization together with the trapezoidal, okay, method. So Crank-Nicolson is the trapezoidal method. It is unconditionally stable, and it means that it converges for all choices of K and H. So using this method of lines, we can write our original partial differential equation using this shape, where the matrix B of K is related to the initial value problem method that we are using. So if we are using the forward-Euler method, as we saw before, our matrix BK would look like this. And for the trapezoidal method or Crank-Nicolson, our BK matrix would look like this. You can actually show this because remember the trapezoidal method is like U1 plus 1 minus UN divided by K, and then here you are going to have 1 divided by 2, and then here your function on UN plus F, your function at n plus 1, and if you apply this to our ODE system, you can see that your BK function will be given like this, okay? So for stability for numerical methods for partial differential equation, we can need another kind of stability definition. So a linear method of the form that I said before, so UN plus 1 equal BK UN plus some vector B is Richtmeier stable if for each time t there is a constant t, c of t, just in the sense that for each time you have to choose a different constant. So for each time t you have a constant c such that this happens. So This notation here is called norm, and here it's a norm of a matrix. We can define different norms. So for instance, the norm 2 of a matrix is the max of the actually I don't exactly remember if it's the norm 2, but like in some norms you can have that these represent the max of the eigenvalues of a matrix. So you're just requiring that the maximum of the eigenvalues of your matrix to be bounded for all k bigger than 0 and integers n such that this happens. Okay, so there is another theorem that's called the Lax equivalence theorem. So a consistent linear method of this form here is convergent if and only if it is Lax-Richtmeier stable. So this theorem is very strong if you think about. So it means that you don't need to prove consistency. So it means that Lax-Richtmeier stability implies on convergence, and the other way around, convergence implies on Lax-Richtmeier stability. Okay. So if there is a constant alpha, so that a bound of the form exists, remember that B of k is a matrix, okay? So we are basically putting some bound on the eigenvalues of this matrix B. So if there is a constant alpha, so that the bound of the form holds in some norm, or at least for sufficiently small time steps k, then we will have Lax-Richtmeier stability in this norm, since this happened. So just remember that we are talking about linear multi-step method. So the linear multi-step method can be seen as for ODE system. It can be seen as a system of linear difference equation. And therefore talking about stability of this numerical method, which is linear, it's related to the eigenvalues of this matrix representing the method. So we would want that the eigenvalues of this system of finite difference to be bounded by 1, and as we have seen before, this linear system has a linear solution, a explicit solution, and this explicit solution, the eigenvalues are somehow some constant times this kind of thing. So this is kind of the some bound for the eigenvalue. So if this happens, we can bound this by the function exponential. We did this to show the stability of the forward Euler method at some point. So this inequality is important because we are finding some bound for the eigenvalues of our method, and it means that for increasing n, we won't have increasing behavior for our methods, you know. So this result is important because bounding this matrix means to bound a matrix with exponent n, and it means it depends on each n, and if we can get a general result, look only for to the matrix B of k, it is easier to work. They say that we have a strong stability if this here happens. So if in some norm, the norm of the matrix B, we have that it is more than 1. So now we are going to start talking about von Neumann analysis. So I'm going to make a pause and you also drink some water, and we come back soon.